Okay, I've hooked up the LED to the same pin 13, but this time it's on obviously the ATMEGA2560, and we have a flashing light. Now, by default, most Arduinos, whether it be the Uno, the ATMEGA, or any of the numerous other ones, come default with the blink sketch already loaded. So I can show you this working, but it really isn't something that I've just gone and uploaded. What I do have on my PC, and I'll put the sketch up next to the screen here while I'm doing this, is I'm going to modify it just so that I'll change the timing just so you can see me uploading to this. You can see here in it already that it's the very basic sketch, digital write LED built in. We already saw in one of the previous videos that the LED built in points to whatever that LED is connected to, which typically is the Arduino pin 13. Now obviously this ATMEGA2560 chip here is not going to be the same pin as what we had on the ATMEGA328 in the previous videos. It's going to be a completely different pin, a whole bunch of internal differences, etc., but yet it's still working, and that's because we effectively have a complete isolation in what pin 13 is. We've got aliases, which is where we have LED built in being mapped to an actual quotes Arduino pin, which in this case is pin 13. But pin 13 in the macro code in the compiler behind the scenes is actually physically translated into the real pin when it compiles the code and uploads the sketch to the device. Now that's quite an advanced topic. I have gone diving into that code before because I did notice on one time that when I ran specific code on here on one of these Arduino 2560s, it ran notably slower than what it did on the Arduino Mega 328P, and yet they were running at the same clock of 16 megahertz and had identical sketches in them. And the reason for that was because there's a lot more hardware inside this chip that has to be figured out by the compiler. So the code, when it was running, took a little longer to figure out which pin it was really mapping to. Now, when you have a sketch like this, where you've got a fixed delay and things like that, those timing differences won't be noticed at all. It's only when you're trying to generate maybe 100 kilohertz or 200 kilohertz square wave or something coming out of the device, that's when you start to notice the timing differences between the two different compilers. Now you can write assembly language for these things too, but again, that's a more advanced topic that we'll do in some future date. Anyway, for now, I'm just going to tweak up this a little bit and speed it up. So we'll change the timing to say, we'll just double it to the 500 milliseconds, so it should blink at twice the speed. I've got to change the board. It's still pointing to the Arduino Uno, so we'll change it to point to ATMEGA2560, and this is going to have a different port. So in this case, it's showing up fully here, so it's COM12. That's all we have to do. So the code is not changed at all from what we were using before. And if I hit upload, you'll see the lights over here blink in a minute once it's finished compiling. It's still busy compiling right now. Okay, it's just finished there. It's used a whole 0 bytes of program space, and that's because it's got 256K instead of 32K, so way more. So it's not even enough to get to 1% of the code, and the global variables is only using 9 bytes, so 0% again. Now it's uploaded, you can see that it's blinking at twice the rate. So I was going to show you how to do something a little more adventurous with this. So first of all, I'm just going to show you with the LEDs what else you could do, and then we'll call it quits on here looking at this kit, and then we will in another video look at maybe how you could create a Christmas decoration. And I have one kind of already prepared that I'll dig out and show you how it works and introduce you to a different type of LED interfacing. We'll be using a little bit of libraries. Again, we're jumping ahead a little bit for that just because of the time of year, but it should be quite interesting to a lot of you, and so we will try and do it. Anyway, let me just grab some other parts and we'll continue with this. Okay, now for the next level of driving some LEDs, I've switched out our red LED here for one of the RGB ones, and I've hooked it up so that it is connected and working the same as before with this blink sketch right now. On the screen I'm showing you a picture here. This is just arbitrarily picked up off the internet, showing the pin out of this RGB LED, and you can see it's like red, a common negative, and then the green, and then the blue. Now all I've done so far is hooked up the red, so we need to hook up the other two, and you shouldn't really put a resistor right on the common. So here we've got the resistor feeding into the red leg. Where it goes into the common, you can but should not put in a single resistor here for all three. If you're only driving one at a time, you would probably get away with it. But if you are driving all of them so that you can have lots of different colors, then you should have an individual resistor for each one. So what we're going to do is we're going to get two more resistors off of our strip and add them into the circuit here. Now, in the previous video, what I did was I just pulled a resistor straight out of the tape. I literally pulled it out of the tape, like, like that. The problem with that, and one of the viewers actually correctly pointed this out, and you get complacent. I've been doing this for years and years and years. Most times you can get away with it, but you still shouldn't do that. And the reason for it is there's glue in between this tape. This is two pieces of tape, and the adhesive can stick to the end of the legs, and therefore when you put it into your breadboard, it gums it all up, and then after a while you might be trying to troubleshoot something, and because it's not working properly, and all it is because there's a bit of glue still on the leg of the resistor, and it's preventing you from getting a good contact. So the right way really of doing this is to get a nice pair of snips. I've got these flush cut snips, and just snip them off at the edge of the tape. Alright, now that one's going to drop out, but I'm going to cut the other end of that off because I know it's got adhesive on it. So I'm just going to trim that off. And once you've trimmed them off, then you know you don't have any adhesive on the resistors. Okay, so thank you for pointing that out and reminding me. I do know it. It's just like I say, when you've been doing this stuff for years and years and years, you do become a little complacent about some things, and that was one of the things that I had become complacent about. So anyway, here's two more 220 ohm resistors. We'll just give them a bend over. I haven't updated any sketches here yet, and we'll just drop these in. One for the green. Okay, that's the other two pins now hooked up. So as you can see here, you may not be able to see it very well, but I have the red in pin 13, the green is in pin 12, and the blue is in pin 11. So what I'm going to do is modify the sketch so that we'll just output to each of those pins in turn. So have to add the two extra initializations. So we'll just copy this one, and we'll say, we'll change this to the real numbers just so you can see 13, 12, 11. So that's red, green, blue going down. And we'll add the extra, first of all I'll just add the extra rights just right there. Actually, I'm gonna, yeah, we'll just do it that way. 13, 12. I'll show you in another video how to make this more readable. So again, 13, 12, 11. So all I've done is added the 2 extra outputs into this little sequence. So if I just upload that, we should get all 3 of them, and which means you're going to get almost white coming out of here. All right. Now obviously we've got RGB and we're getting a very, well, it's not quite white because full intensity red, green and blue does not give you white. You've got to adjust them a little bit. That's more of a bluish color there, almost a turquoise. So I'm going to put a delay between each one, and we can make them go on one at a time. So if I put it right 13 high, 12 low, 11 low. We're just going to do a very crude sequence here. Delay half a second. We will then do 13 low, 12 high, and 11 low. Another delay. And we're going to repeat this now. So we've got the 12 high. Now we're going to make that one low. This is not the most efficient way, but it makes it easy to understand. And we'll make 11 high, delay 500, and then it's going to go back and do 13 high again. So what it should do is ripple through red, then green, then blue, with a half a second delay between each one. So let's just quickly compile that. You see all I did there was I just added the extra 2 pins. I'm changing the state of the outputs on each delay. So upload that. Now we're going red, green, blue, red, green, blue, red, green, blue. Okay, so that's now modified. So now we're driving an RGB LED. Now we can actually, if we used what they call PWM outputs, I'm not going to go into that in this video because it's a little bit more advanced. But if we use RGB with PWM, then you can start doing any color, each PWM, even if there are only 8 bits of resolution, so 256 different pulse widths, then that would give you 888, so 24 bits, which is I think 16 million plus different colors. Okay, and that's a lot. That's how a lot of these RGB strips that you might see on Amazon, eBay, Banggood, etc. Can work. Now obviously if you've got a strip of 60 LEDs, then using 3 wires per LED, I mean this thing has 56 general purpose IO lines on it, but even that wouldn't be enough if you had 60 LEDs in the strip, maybe for a Christmas tree light, to control all of them individually like that. You would have 60 times 3, so 180, 60, 120, yeah, 180 lines coming out just to drive this, and that's not very practical. So LED strips have a chip built in with the LED that you can talk to via a serial bus, or some of them do. And so what I'm going to do in the next video as part of the Christmassy type thing is show you how to use one of those in as simple a way as I can. Now before I go on this one, I've modified this sketch to say 12, 13, 11, 12 and 13 RGB, and I'm cycling through them here. I'm going to just unplug this ATMEGA2560, plug in the Uno R3, upload the exact same sketch untouched, and you'll see that it'll do exactly the same thing without any code changes. And that's one of the advantages of using the Arduino IDE. I will have to tell the Arduino IDE that I've got an Arduino Uno R3 instead of an Arduino Mega. Then that will tell the compiler the adjustments it would have to do behind the scenes to talk to the correct pins. So let me just grab the Arduino R3, and then we'll switch it out and upload the sketch and see what happens. So here's the R3. I'm going to unplug the ATMEGA2560. I'm going to take these 3 leads, remember they're on 11, 12 and 13, and I'm going to plug them into 8, 9, 10, 11, 12, and 13 on here. Unplug that, don't need that. I need the ground. That one's not being used right now, so plug the ground in. Right there. That's all the connections we need. Now, there was a sketch left on here that might start flashing one or two of the pins, but it certainly won't be doing what we expected. So that's it powered up. Right, because if you remember at the end of the last video on this subject, we had it alternating between two LEDs, and that's what you can see happening there. Now, I'm going to re-upload this sketch. I need to tell it that I've got an ATMEGA, an Arduino Uno, sorry. So we're just going to click on Uno. We're going to pick the correct serial port because it's not on the same serial port, which is on 13 in this case. And we're just going to click upload. I'm not going to change anything else. It's going to recompile. There it is uploaded. Now it should be doing the same thing. And there we go. So you can see, no change in the code. All I did was tell it the different board that was connected, uploaded the same sketch, same pins, even though they're completely different processors, and it's working perfectly. All right, same timing, same everything. All right, so what we're going to do now is call it quits for this. I wanted to just go over the main differences between this kit and the earlier kit. So as you saw at the very beginning, you've got more hardware. You have a much more capable controller with the ATMEGA2560. These, just out of interest, these are used to drive things like 3D printers. A lot of 3D printers on the market that you can get, and they're not talking about the really high-end ones that run Linux or something like that, but some of the lower-end ones, they still use ATMEGA2560s to drive the 3D printer. That shows you the capability that actually is in one of these boards. Now, a board like this, I've shown probably a couple of years ago now, I was actually using one of these to drive a CNC machine in my garage. I built, under tutorials, a CNC machine, and I used an Uno R3 as the controller. I was sending it down G-code to instruct it what to do with stepper motors, and it was controlling an X, a Y, a Z, and E-stop, so emergency stop, and end-stop sensors all on this one. So even one of these is quite capable. Now, using one of these, is better, and the reason for that is when you're using something like a 3D printer, you've not only got the 3 axes of motors to control with their end stops, you also have temperature sensors, bed heating, hot end heating. You have a 4th stepper motor for driving the filament feed. So there's a lot more going on, so you need more I/O in order to be able to control it. This R3 is enough to be able to drive a basic CNC machine, but it doesn't have enough I/O to go beyond that, at least not without adding a lot more extra hardware. And I'm not talking about the stepper drivers, I'm talking about to give it extra I/O lines to do something. And you would run out of flash space in here as well. Remember, this has only got 32K of flash. This has got a 256K of flash. This only has, I think, 1K of electrically alterable read-only memory, so EEPROM, or electrically erasable memory. This has 8K, 8K? I got a data sheet right here. Let me just bring it up on that one. So you can see here some of the features that are on this new microcontroller. 32 8-bit general working registers, 16 megahertz, that's pretty much the same as the other one. In our case, 256K bytes of self-programmable flash, that's what we were writing to when we used the Arduino to upload. 8K bytes of internal static RAM, 4K bytes of EEPROM. The ATMEGA2560 only has 1K of EEPROM and I think 4K of internal RAM and only 32K of ROM, like programmable flash, sorry. So that's right there, that's a huge increase. Now the other parts that it has, it's got Q-Touch, so you can have touch sensing on it. Huge extra range of peripherals, including 12 PWM channels, even 16-bit. 10-bit analog to digital converter. Only in this case we've got up to 8 or 16 channels, depending on the chip. We've got the biggest one, so that gives us 16 channels. 4 UARTs inside, so serial interfaces. Analog comparators, etc., etc. When we go down the I/O lines, we've got the biggest chip here, so we've got 86. Sorry, I said 50 odd. I read the wrong one before. 86 programmable I/O lines on here. On the 328, we've only got maybe 20. And the other part that we have here, by the way, if you wanted to run on batteries and things, these will run down to about 1.8 volts. But if you look at this bit of the table right here, you'll see that if you're running it down that low, you can't go above about 4 megahertz. Sorry, if you're running at 1.8 volts, you can't go above, yeah, that's the wrong chip there, above 2 megahertz for the 2560. If you are running at 8 megahertz, you have to be at minimum 2.7 volts. So if you're using a 3.3 volt supply, for instance, you can't run at 16 megahertz. For 16 megahertz, you need to be running on a 5 volt supply, okay, which is what we're getting off the USB interface here as well. Yeah, so that's the basics for one of those chips. Here's the pin layout for it. As you can see, it's 100 pins on there, and a lot of them are dedicated to GPIO lines that you can, there's internal mapping that allows you to configure what those lines are going to do. And part of us doing those first few statements in the Arduino IDE, for instance, let's go back up to it, pin mode is we're actually writing to those mapping registers and setting it up to be an output instead of an input, or a PWM or an analog, depending on what pin and what you want to do with it. They have multiple functions. Anyway, yeah, so the kit, I think, is a really nice kit. They give you a huge range of parts to play with, and we will be, as we go through, now I've got both kits. I'm going to be showing you different code, slowly increasing the type of code that we're doing, and when we're done, I'll be showing you it working on both of these where possible. At some point as we're going through, we will probably end up running out of programming space on here, in which case we will just have to be working on the bigger one. So either of these will be great project kits for sort of like teenagers, young engineers, students at college and things like that, to learn how to program at a effectively real-time programming level, as opposed to using something like a Raspberry Pi. I mean, that has its own benefits as well, and I'm going to be doing some videos with that too, but not part of this series. They may be running in between some of these videos, but you can do a lot of very low-level things with these, and they're not very expensive. Now, one of the things I will also show you how to do is actually build your own one of these if you wanted to put it onto a breadboard and have a minimal number of components. I'll show you how you could set one of these up, flash your program to it, and then have it on your own little board with a dedicated application. So the kits I'll provide links to in the description of the video, and if you like this, obviously give it a thumbs up. If you don't, then don't. Please click through the links if you want to buy one for yourself. It just lets the in this case Elegoo know that people are watching my videos, and it may help me get some commission or additional products from them to share with you in the future if they know that people are actually watching my videos. So anyway, I will see you in the next video where we're actually going to take a little bit of a leap forward, and I'm going to use some LED strips to show you how to make some Christmas decorations. And I will see you there. Okay, bye.